Hello and welcome back to this channel. Dear students, this topic is signal energy and signal power. In this session, we will discuss what is the meaning of signal energy, what is the meaning of signal power, as well as we will discuss the energy spectral density, that is ESD, and power spectral density, that is PSD. We will also discuss the comparison between energy and power signal. We know that in case of communication, signals are used to transmit the information from transmitter to the receiver. So, to do the analysis of signals, it is required to calculate energy or power of that signal. So, let us first talk about energy of a signal. There are two broad types. One is energy signal and another is a power signal. So, first part is energy signal. Actually, energy term represents the total strength of the signal over the time period. It measures total amount of energy contained in that signal. You can define energy signal like this. If you calculate the energy of some signal and if that energy is finite, it is not infinite. If calculated energy of a signal is finite, then it is energy signal, provided that its average power is 0. So you can well define it like this. The total energy of an energy signal is finite, but average power is 0. Now mathematical equation to calculate the energy of a signal is E, that is energy, is equals to integration minus infinity to plus infinity mod magnitude of x of t square dt. Here x of t represents the amplitude of the signal whose energy you want to measure. Now there are certain important characteristics of this energy signal. Energy is always between 0 to infinity. That means energy is finite for a particular time period. It should not be infinity. Second, it exists for finite time period. It is not existing for infinity time period. Then it is mostly all the energy signals are non-periodic. So it's very simple. Rather, take it as a simplest clue. If you just want to take a judgment whether the signal is energy or power signal, if it is non-periodic, for example, a pulse signal, a single pulse is there, it is not repeating, it is not periodic, then in that case, it is energy signal. So most non-periodic signals are energy signals. And fourth characteristic is average power of energy signal always tends to 0 as time t goes on increasing. So these are four important characteristics of energy signal. Now, some examples of an energy signal, as I just now mentioned, a pulse is a very good example of energy signal. Then any kind of transients, then switching waveforms, then radar pulses. These are good examples of energy signal. As an example, I have shown one rectangular pulse whose width is TP. This is the rectangular pulse which is non-periodic because it is only one pulse. It is not repeating till infinity. So it is energy signal. If you take Fourier transform of this, then you will get this type of waveform. It is called a sync waveform. Now, this time period is Tp. So, this particular portion, I am talking about this portion. This is the diagram with respect to frequency. Rather, it is also called the spectrum. So, this particular width represents the useful width of that signal. And it is 1 upon 2 Tp. Now, next part related to energy is energy spectral density. Actually, ESD, that is energy spectral density, is a graph which shows the distribution of energy for a given frequency range. So, it gives distribution of energy across frequency. ESD is mathematically expressed as mod of x of f square. Do remember, x of f represents Fourier transform of given signal x of t. So it is this two vertical line, we know it represents the magnitude. So it is magnitude squared response of x of f. Now, important characteristics of ESD: the total energy is area under the curve of ESD. That means if you plot the curve of ESD, ESD is distribution of energy across the given frequency range. If you calculate the area under that curve, and we know that area under curve is integration. So if you have a graph of ESD, if you calculate area under that curve, that means if you perform integration, that will give you value of energy. So total energy is area under curve is integration. That means if you know EHD, if you have the graph of energy spectral density, perform integration, generalized limits minus infinity to plus infinity, mod of x of f square df. We know mod of x of f square represents EHD. Then actually EHD determines the bandwidth of the signal. And third, it is mainly useful for pulse and transient signal analysis. So this is about energy and energy spectral density. Now next part is power signals and PSD, that is power spectral density. Just now we discussed ESD and energy of a signal. What we discussed, usually or mostly the non-periodic signals are energy signals, and energy signals exist for finite time duration. On the contrary, power signals are existing for infinity time period, and mostly periodic signals are power signals. So power signals represents average strength of a signal over infinite time period, whereas we discussed in case of energy, it represents the total signal strength for a finite time period. This represents average strength of a signal for infinity time period. Mathematical equation is P, that is power of a signal, is 1 by 2t, where this big T, capital T, indicates the period of a signal. So 1 by 2t integration minus t2 plus t mod of x of t square dt. Likewise, the energy signal x of t represents amplitude of a signal. Then power signals are having infinite total energy and finite average power. Important characteristics are, if it is a power signal, energy is infinity because average power is finite. So energy is infinity and the signal exists for infinity time period. Then power signal is finite, that means value of power is between 0 and infinity. Mostly periodic signals are power signals. Examples of power signals are sine wave, square wave, triangular wave, and so on. Then PSD, similar to ESD, PSD is power spectral density, which represents the curve that explains the distribution of power over the given frequency range. So distribution of signal power across frequency gives us an idea of power spectral density. Mathematically, PSD is given as limit as t tends to infinity, mod of x of f square upon 2t. The power of a signal can be calculated from its PSD curve. It is very much similar to the ESD, what we discussed in case of energy spectral density. If you take area under the curve, that means if you take integration of ESD, you will get energy. On the same lines, if you integrate, that means if you calculate area under PSD curve, that means if you are integrating from minus infinity to plus infinity of PSD, you will be getting the value of power of a signal. Then PSD is useful for noise analysis, then calculation of bandwidth, then filter design, and so on. So this is about power and power spectral density. Now let us discuss the comparison between energy signals and power signals. So this table shows the comparative analysis between the two. The features, first feature is energy. In case of energy signal, the energy is finite, whereas if it is a power signal and if you calculate energy of a power signal, it is infinity. Then average power, if it is energy signal, its average power is 0, whereas if it is power signal, its average power is finite. Next, duration, we discussed that mostly the energy signals are for finite time duration, whereas power signals are for existing for infinite time duration. Then nature of a signal, mostly energy signals are non-periodic, whereas most of the power signals are periodic in nature. That means they are repeating after certain time interval. Then spectral measurement, for energy signal to measure the or to do the analysis of spectral, ESD, that is energy spectral density, is used, whereas for the power signal, for the spectrum analysis, PSD, that is power spectral density, is used. So this is about the comparison between energy and power signal. So dear students, that's it for today's session. Thank you. Thanks a lot for watching this video.